Let's do an example of Biot Savart's law and doing an example where we integrate over the entire current here. So remembering Biot Savart's law is the magnetic field B is equal to mu naught over 4 pi, the integral of I dl cross curly r hat all over curly r squared. So let's take as our little bit of current here, or our current loop, just this half circle of current with a radius r and a total amount of current I running along it. So we want to do this integral over this little piece of current here, this piece of bent wire. So we should first figure out what dl is. I is just the current I, it happens to be a constant, so we're just going to put it there. But dl, well, dl is pointed in the phi direction, and so we should have r d phi phi hat for dl vector. So r d phi is the little bit of length, and then phi hat gives us the direction. Now we need to worry about curly r vector, curly r hat, and curly r squared. And so our curly r vector points from the little bit of current, the little bit of length, to the point that we're interested in the magnetic field at, point P here. And so our curly r vector is given here. If we give that in cylindrical coordinates, then curly r vector is minus r s hat. That conveniently has a magnitude of just r, so that r hat, curly r hat that is just minus s hat, just pointing in the minus radial direction. So we can put that into our Biot Savart's law. So for curly r hat, we put minus s hat. And then for curly r squared, we put r squared. Now, virtually everything in here is actually a constant. The thing that we're integrating over is the phi direction. So almost everything here is a constant. We can do some cancellations and pull some things out of the integral. There's a minus sign from the minus s hat, so we're just going to put that minus sign out front. So we get minus mu naught I over 4 pi. There's a 1 over r. And then the integral from 0 to pi of phi hat cross s hat, integral d phi. So I didn't want to take the phi hat cross s hat out of the integral just yet because we need to figure out what that is, what phi hat cross s hat is. It could depend, for instance, on the angle that we're at. And so we need to be a little bit more careful there. Well, it turns out that the cross product between phi hat and s hat is something really nice in cylindrical coordinates. So if you remember our definition of cylindrical coordinates and unit vectors in cylindrical coordinates, phi hat cross s hat will give us minus z hat, it turns out. So we can just replace that phi hat cross s hat inside the integral with minus z hat. And the z hat direction always points in the same direction regardless of your angle phi. It doesn't matter where you're at in the cylindrical coordinate system. You're always going to have z pointing in the same direction. And so we can pull that out of the integral now. There's a minus sign that cancels a minus sign out front. And so we just have mu naught I over 4 pi, 1 over r, z hat, and the integral from 0 to pi d phi. Well, that integral is just pi. And so we get for our final result for the magnetic field is mu naught I over 4, 1 over r, z hat. Now we can check this just real quick to use our right-hand rule to see the direction, make sure the direction makes sense. So if you put your thumb along the direction of the current and curl your fingers around the wire, then your fingers will point in the direction of the magnetic field at point P. And that seems to be coming out of the page, and that is the z hat direction. So at least our direction matches.